Hello there. Sheridan, Kiana, Kyle, I'm happy to see all of you here. I got through your grading your work, and I'd say overall, this is really, you're doing just great. You should all feel pretty good. There are a couple corrections you probably saw, like minor steps. And if any of you want to resubmit, my goal at this point is just to see that you understand these concepts. And so if you're able to solve these problems and get to the correct answer and show that it's making sense to you and you've interpreted right, then you're in good shape with meeting the goal. Any questions before we get started? Let me just ask you to say hi to me so I know that you can hear me. Thanks, Sheridan. I see Ashley has jumped in here. I'm pleased to see you. So what I'm going to do today is I'm going to start out by doing one problem in the one sample t-test. Everyone who's here, you guys are in good shape, well along the way to showing that you're done with this, that you've met this expectation in chapter 7A. And there were just a couple of minor problems. So I'm going to just work through one of them with you and give you a couple of recommendations. And then we're going to jump into the new content, which you'll find is really similar to what you've just done. So if there are no questions, okay, let me share my screen and I'm going to just work through some problems with you. Okay, so I'm actually going to go through one of your exact homework problems. And so I've written it here. And let me grab the data here too. No, I don't need to grab the data. So we're looking at this one where these healthy people were taught these breathing exercises, and they had resting heart rates of 62, 70, 81, 67, and 58. And we're going to test the hypothesis that these heart rates were lower than the average heart rate of 78 for people in general. And we're going to work it just like we did before. The first thing I'm going to do is write the data out in a grid because that always works better for me. So we have person one. I won't write an S because that will confuse us later. Let's call it person one. Person two, person three, person four, and person five. We know that their scores, in this case, their heart rates, and I'm going to just make an X there then. Their heart rates as given in the problem are 62, 70, 81, 67, and 58. So if you want to redo this problem as we're going and use this as an example for any corrections you're going to make in your homework, then that's just fine. All right, so this is the information that we're given. And let's just start by getting the basic information down that we're going to need to know. We did this last time. I find it to be a good way. This is what I do when I'm working the problems. So I'll just do it this way with you too. So the basics that we know we're going to need to know N. We're going to need to know good degrees of freedom. We're going to need to know the population mean. And we're going to need to know the sample mean. So let's calculate all of this out. Please write in the chat box, what does the N stand for in these types of problems? Hi, Kyle, I just saw your message. Oh, no. Oh, cold. I'm so sorry you caught it. Get those shots, guys. get those shots, get immunized, be safe that way. And if any of you want to meet with me independently to work on these problems, I really want you to do it, get through it. Let's just remind ourselves, what does the N stand for? Please just write an answer to me. Yeah, then I see that, Sheridan. And Kyle, very good. So yes, I'll just write this out here. Anytime you see the N in statistics, it always will stand for, always stands, I'm putting it in the chat, for the number of individuals in the sample. And that's how the best way to state it. And that's what I've written it for you. So in this case, our N equals 5. Degrees of freedom is N minus 1. Minus 1 equals 4. The population mean is given to us, and it is, I made it really small here, equals 78. That's from the problem, and we have to calculate our sample mean, and that's a simple calculation, the sum of all the scores divided by N, which in this case equals, let me pull up my calculations. In this case, equals, correct problem, 338 divided by 5, and that is equal to 67.6. So there's our basic information. So let's go ahead now and begin with our steps. Let me see, I think I'll have room over on this side to begin our steps. So maybe I'll skip to blue for our steps. So step 1, let's make sense of the problem. And we know that population 1 are the people with breathing exercises. When you're doing your work, people, I encourage you to have each problem on a fresh sheet of paper. That way you won't get so tiny. And organize your paper a little bit. The way I'm doing it is a good way. We are comparing the people who've had these breathing exercises with people in general. So this is basically what we're doing. What are we comparing? Our DV is heart rate. Sorry about that work there. We are looking to see if heart rates are lower. So this is what we're looking for. Average heart rate is the DV, and we're looking to see if they're lower. So we're going to be doing a one-tailed low. And I'll just write up here that we're looking at P value 0.05. Now we have it written there, so we don't have to go back to the problem. I got that right here. And we know that the hypothesis, the research hypothesis, is that the mean scores, the mean heart rates for population 1, so the mean for population 1 will be lower than mean heart rates for population 2. And the null hypothesis is just the reverse of that, that the mean heart rates for population 1 will not be lower than the mean heart rates for population 2, or we could simply say the mean for population 1 is equal to the mean for population 2. And this means, of course, drawing out the distribution, that we're going to have something like this, and that we're looking for a value in the lower tail. And if we have and we're looking for to be specific, we're looking for a sample score, a sample mean to be in the lower tail. Okay, a little messy, but I think it looks good. So let's continue on. No questions, I don't think, on step 1. You guys all seem pretty good with that, but let me pause a minute and ask while I set up step 2. We're going to describe the comparison distribution. What are we comparing these guys who have the breathing exercises with? Well, we're going to compare them with the mean scores for just people in general. And so we need to describe that. We can describe it in terms of center, in terms of shape, and in terms of spread. So the center, remember, when we talk about step 2, we're always talking about the comparison population. So we're going to use mu. The mu is given, and we wrote it down already up here. The mu is 78. So we're comparing our sample with whatever mean they have. We've already calculated it. And we're comparing it with this mean of 78. The shape, we're going to use a normally distributed T distribution. T distribution for the degrees of freedom. Remember, we can no longer, one of you did really good work, but you used the cutoff points for the Z distribution. We can't do that. We always have to use the T distribution now and look at the degrees of freedom, which in this case is 4. And the spread, we're going to need the standard deviation, the estimated standard deviation for the distribution of means. And so we know now we can already plop in here one piece of information. Of course, we know our Z scores are always, our standardized scores are always going to be 0. I'll just lightly draw the lines. Probably 1 is right about here, 1 standard deviation. Maybe 2 is right about here. Maybe -1 is right about here, -2 right about there. We know those from before, but we also now know that for our comparison distribution, we have a mean of 78. And we have to figure out the standard deviation for the distribution of means. So let's move forward. And the first thing we have to do is that big step of estimating. And estimating, we're basically just estimating the standard deviation for the distribution. We're estimating the variance, actually. We don't even have to go to the standard deviation. So let's just put estimate the standard deviation, the variance. I said that for the second time, excuse me. Estimate the variance, which is S squared. So let's go ahead and do that. We know that the variance requires 2 pieces of information. It requires the sum of squares. And then we'll go ahead and calculate the variance by going sum of squares divided by degrees of freedom. So these are the 2 pieces of data that I generally get. The sum of squares is simply the sum of all those deviations squared. One person made a mistake of adding x minus m. Let's go ahead and solve this out, and then let's look at why we're looking at differences. So basically, when we think of a deviation, we're thinking of like how far it is off center. Like if you have a teenager and you say this teenager is engaging in deviant behavior, what you mean is behavior that's outside of the realm of what's normal, right? And so that's what we mean when we think about numbers too. We're thinking about deviations. How far are these numbers off of what's considered normal? So we'll consider normal to be the mean. And in this case, we're estimating for our sample. So our mean is 67.6. And I'm just going to write it in here, our sample mean, because we're going to need it for all of them. 67.6, 67.6, 67.6, and 67.6. So we're subtracting our sample mean right down the line here. And our deviation is going to be the difference, right? How far is it away? So we don't want to add, we want to make sure and subtract. So this is our deviation, which is x minus m. Now, I really encourage you to do as I am and write these out by hand or use Excel, but don't try and type all these in. It's quite tedious, actually. So now we're going to subtract x minus n, so 62 minus 67.6, which equals negative 5.6. 70 minus 67.6 is 2.4. 81 minus 67.6 is 13.4. 67 minus 67.6 is minus 0.6. And 58 minus 67.6 is minus 9.6. So these are the deviations. Remember our little reminder of what SS stands for. I'm going to put a note right here. SS is the sum of squared deviations. That's what SS stands for, the sum of squares or the sum of squared deviations. So right now we have all of the deviations. X minus m refers to the deviations, but we need to square them in order to figure out our sum of squares. So let's take and figure out our deviation squared, or x minus m, which we've already done, squared. So x minus m is here. If we square negative 5.6, multiply it by itself, we get 31.36. If we square 2.4 by multiplying it by itself, we get 5.76. If we square 13.4, we get 179.56. If we square minus 0.6, we get 0.36. And if we square minus 9.6, we get 92.16. Big numbers, but doesn't matter. We can work with them, especially if we're doing Excel. So our sum of squares is just the sum of all of those. So we're going to add all of those up. 31.36. I'm not going to write them all out. I'm just going to write a couple of them. 31.36 plus 5.76. I'm going to write dot, dot, dot. And if I add all of those up, I get 309.2. And so that is the sum of all of these numbers. So I'm going to take orange. I'm going to put this in orange and show that it is just the sum of all of these. All right, next step is quite simple. We just need to take our sum of squares and divide it by degrees of freedom. And this is the point, remember, where we are estimating. This is the only point that we're going to estimate right here. And that just means we divide by degrees of freedom. So SS divided by DF is 309.2 divided by 4. And our variance then is going to be 77.3. So that's our estimated variance. And so if we just had a sample of 1, we could just use this right here, take the square root to get the standard deviation and move forward. But we cannot compare apples with oranges. If we have a sample of 5, we need to compare it with means for other samples of 5. And that's where we have to go to the next step, which is to calculate, no longer estimate, calculate. And that means we're not going to use degree of freedom. We're going to use the actual number. We're going to calculate the standard, well, let's see here. The standard deviation for the distribution of means. And we just write it as estimated standard deviation. We've already calculated that for the distribution of means. And so that's a quite simple calculation. We've done it before. All we're taking is the variance divided by n. So first we're going to figure out the variance for the distribution of means. And another way of saying this is variance for the distribution of means is just s squared divided by n. And in that case, our solution is 15.46. We don't need the variance, though, to put into this chart. We need the standard deviation. So the standard deviation for the distribution of means is the square root of the variance for the distribution of means. And that equals 3.93191. And I'll transfer it over here now to our answers. Nice and neat, so it's easy to read. 3.93 is up to 2 decimal places. And I will mark it probably with just 1 decimal place in our chart. Does anyone see any computational errors that I've made? If you're following along, because this often happens to me.
On the calculate standard deviation, how did you get 15.4? Is that?
Sure.
What's that?
Excellent. I took this formula, variance divided by n. So the variance we already had right here. Let me circle it. This is the variance. And I divided by the number in the sample, which is up here. So remember, all we're doing is we're taking the variance for this individual population and we're dividing it among the number in the sample, among 5, because we have 5 in the sample. So I'll just write out the formula here then. I just looked up to what I had solved, which is s squared. And so it was 77.3 divided by, and the sample size was 5. What do you think? Does this make sense, Kyle?
Not really.
Okay, what can you help me understand? What is it, the s squared that looks funny to you?
Yeah, because what I did was after that step, I did 309.2 divided by 5, and I got 61.84.
Okay, this is where you went wrong. You combined the 2 steps into 1. We have to do these as 2 separate steps. First, we estimate the variance for the population of individuals. So this is the first step that we have to do. And that, when we estimate, we divide by degrees of freedom. So you have to do these 2 formulas in order to estimate the variance. First, the sum of squares, which you did correctly, it sounds like. And then the variance, but we're estimating it, which means we're taking it sum of squares and dividing by degrees of freedom. And this brings us to this 77.3 is the variance for the distribution of individuals. Distribution n equals 1. Sorry about that noise. Someone's doing some work next door. Sorry, I'm going to just wait. So the next thing we have to do is we have to figure out what's the variance going to be for n equals 5. And that's what we're doing in this step. So here we're estimating the variance for n equals 1. Now we have to calculate to get n equals 5. So then we take this variance that we calculated and we divide by n. So we're first dividing sum of squares by degrees of freedom, and then dividing that answer by n, which is what we did here. So we're just taking those two steps. So we the second step is what we did with the z distribution. It's just finding out the distribution of means. So it's just the same as before, except we're using this estimated number instead of a calculated number that's given to us.
Okay, I see where I went wrong.
Okay, good. I'm glad. That's exactly why we do the practice, so you can see where you're making a mistake and going wrong. Does anyone else detect any sort of problems that I did here? Any mistakes that I made? Believe me, my work is not perfect, as you probably know. Okay, let's just write these numbers in so we know we're making good sense here. So if we were going to fill these into the distribution, we knew that our comparison distribution has a mean of 78 and 3.93 going up. And you know, just for the sake of estimating, so I know if I'm in the right ballpark, I'm going to write 4, 78 plus 4. I'm going to estimate 82 and 74. So now when I'm looking at my raw score, my sample mean, I know my sample mean is 67.6. So I know this is kind of making sense on this distribution. We'd have about 70 here. We'd have 82 plus about 4 would be 86 here. So now we kind of know when we get our answer if we're in the right ballpark. So continuing on to step 3, we're going to find the cutoff point. One person made the mistake of using the cutoff point for the z distribution. Remember, we need to go in and find the cutoff point for the t distribution now. And I gave you a really nice little calculator to do that with. So let me pull it up for you. I bookmark all my things. So here's the t critical value calculator. So all you have to do is fill in the information. We were told the p-value is 0.05, and we know that we had 4 degrees of freedom. So we'll enter those 2 pieces of information, hit calculate, and this tells us what our cutoff points are. So we were looking for, let me check back now to make sure I don't make a mistake. We were looking for, when we look at our tails, oh no, don't do that, don't do that. There we go. One-tailed low. Looking at this t-value calculator, I'd just like to know if you guys know what to do with that. If you know what right-tailed is, if you know what the cutoff is going to be now. So right-tailed is for a one-tailed t-test with degrees of freedom equals 4, and that's if we were looking for something in the high end. What is our cutoff point going to be? I'm going to write this question out. I'd really love to see answers. What is our cutoff for one-tailed low? Based on what we see.
Is it a negative 2.13?
Sheridan, Kyle, you're correct. I hope that the others of you who are sitting in see why that is. So remember, it's going to be the same number. It's going to be the same t-score, whether it's high or low. It's just that if it's low, it'll have that negative sign. So in this case, they're looking for a t-score that's on the right, or picture the distribution, the high end of the distribution. We're looking for a t-score that's on the left or on the low end of the distribution. So let's go back to our image and fill that in. So to be specific then, our cutoff point is going to be minus 2.13, which is going to be right about here. I say that because I can see the 2. Minus 2.13 is our cutoff, or a critical value, as they say there. And this shaded region will be the critical region. So we need, in order for this to be significant, going back to the problems, in order for the breathing exercises to have a significant impact on heart rate, according to this analysis, we need the mean heart rate to fall in this shaded area. That's the question we're answering. But we have to put some numbers to it and be strict. So we know that our cutoff point using for one-tailed low with alpha, we can say equals 0.05. That's just our probability level, equals negative 2.13. That's our cutoff. Step 4, one person missed this step. Step 4, we have to calculate our t-score. So all of this work right here was for step 2. Calculating the spread, to be specific. So all of that was for step 2, but now we're in step 4, we need the t-score. So let's kind of maybe choose a new color since we're in step 4 now. Step 4, calculate. We're not estimating anything anymore. The t-score. And the t-score is just the sample mean, what we're comparing in population 1 minus the population mean. This is population 2, and we're just dividing it by this nice standard deviation for the distribution of means. And so if we do this math, we go t equals, the sample mean is 67.6 minus 78 divided by 3.931921. I wrote out all these numbers because when we're calculating, we want to use all of them. We don't have to write them all down for our answer. And this would equal minus 10.4 divided by all of that 3.931921. And that equals minus 2.6502. And so in step 4, I can write my answer, t equals 2.65. I'm not calculating with this, I'm just writing my answer. So I use 2 decimal places. And I'm going to place this score up on our little image here. I think I'll use purple. Sorry, I forgot the minus sign. Minus 2.65 would fall outside of 2.13. Here's 1, here's 2, here's -3, and here would be our sample score, which would be negative 2.65. It falls within the shaded region, and it is to the extreme of the cutoff point. And so we're going to draw a conclusion that what? Let me write that in the box. What is our decision? First our decision, and then we'll conclude. Are we going to reject or fail to reject the null hypothesis? And
Reject.
let me, yeah, what did you say, Kyle?
We reject it.
Okay, you're correct. Why do you say so, Kyle?
Because it's outside of the cutoff point.
It's outside the cutoff point. Yeah, it's further to the extreme, further into the tail. It's in the shaded region. We are going to reject the null hypothesis. Let's reject it by crossing it off. We reject it. The only thing left standing is the research hypothesis. So now we just have to write this out in words. So we would just write mean heart rates. That's what that mu means. So mean heart rates. You guys did a good job with this, by the way, and all the problems I looked at. Mean heart rates for people who did breathing exercises. Now we're explaining this in words, right? CISES were lower than mean heart rates for people in general. And you have to write out the statistic. I did deduct even if you wrote this perfectly, but you didn't include the statistic, I did make a small deduction. You need to do this because this is what you'll see in the research. So first you're going to put the t-score, then remember in parentheses right here, you write degrees of freedom. And you can write out degrees of freedom or just write the 4. Other researchers will know what this means. Then you put the t-score, negative 2.65, and then you tell that it passed your test. The probability of getting that score is less than 0.05 or less than 5%. And that's how you write the statistic. So that is the solution to problem 2. So you can all get that one correct. I'm wondering if you have any questions about this before we move on to our next content. And I'm going to give it a pause a minute while I get that problem set up. Please type in your questions or indicate to me in some way what your questions are. And I'm going to try and hold a study group on campus where we can work through these for those of you who are far behind. If it's just 1 or 2 of you, we'll see where the best place to do this is, but I want to work through this with you. So I'm hoping to have an in-person study group here. But in the meantime, any more questions on the 1 sample t-test?
Can I resubmit this problem so I
You
can
can
get
resubmit anything. Yes,
Okay.
what I want to see is that you get it. And I
Okay.
will add one more thing. I think the Excel was a help to some of you and a barrier to others. And if you don't get the Excel part of it, then do these problems by hand. That'll be just fine. Just make sure you show your work. And I really recommend you do these by hand and don't type if that's possible for you. It's just so hard to do these if you're typing. I would like to hear from everyone that you have questions or you don't have questions. That would be good. And I'll pull up another problem for us. Okay, so we're going on to a new concept today then. And the new concept is really similar to the old, to what we've been doing. So I do have all kinds of lectures with slides that I've posted up for you on this, but I'm going to just go through it with you on paper. So I'm going to, is it helpful to you at all if I save this whiteboard? And
yes.
okay, so that is helpful to you. Then let me copy that and save it before I delete it. Gotta get it real small here. A bit smaller. Now I should be able to grab it. I think you can expand it though. I think the resolution is sufficient that you can expand it. I just need to get it to fit on my screen in order to copy it. All right, so let's close that out. Let's clear the screen. So what we're going to start working with now are just situations that most of you often think about when you think about these problems, and it's where we have 2 sets of scores. So let's imagine now that we have, we really want people to start wearing masks, all right, in public. Let's say that we have, we're not going to have another wave. Let's say that for whatever reason, it's really important that people start wearing masks. And so we're just wondering, we're going to give this mask program a good try. We're going to just ask the question, do people, I'm going to make an adjustment to my system here for a minute. There we go. Okay. So we're going to ask, do people who participate in a mask awareness program. Wear masks more often than people in general. And as I write this problem, I'm actually going to change the premise because we'd have to work with a proportion here. So I'm going to just change the premise a little bit. And I'm going to say, do they have a better attitude toward masks? I'm going to change the dependent variable to people who participate, and I'm going to type the problem out so that we can underline things neatly. So let me just do this over again. I have the data already. I didn't write out the problem. So let me just write out the problem here with my typing. So here's the problem. Do people who participate in a mask awareness program have a better attitude toward masks than people people who, it's always awkward to phrase it in this kind of problem, so I'll show you what I mean in a minute. But better attitude toward masks than people whose attitudes did not change. And so the reason that I'm stating the problem in this odd, awkward way is because we're looking at before and after scores. So let's imagine when we did this, that we have before scores for their attitude toward masks and after scores, and that the data you're given looks something like this. So let's say that before, let's give ourselves 5 people. So here's person 1. Here's person 2. Person 3. Person 4. And person 5. And the data that we have for these people is a little bit different. Actually, let me copy it down here so it's a little neater. So what I have here are before and after scores for all of these people. So here are their scores. So you can see what we're looking for now is a change. We're looking to see, did our mask awareness program change the reactions of these people to the masks? Is their attitude different than it was before? And so you can see that the crux of the problem is a little bit different here than what we've been working with. So this is our first person. I'm just going to write it here anyhow, so we have it. Here is our first person. So before they took this program, their attitude was 15. Afterwards, it was 19. For the second person, before they took this program, their attitude was 14, and afterwards 17. Our third person, before they took the program, their attitude was 12, and now it's 11. Our fourth person had an attitude of 16, and it did not change. And our fifth person had an attitude of 11 that increased to an attitude of 15 after the program. And we want to know, well, is this program worthwhile? Should we bother with it? So let's see how we would approach a problem like this. We're looking for difference scores or change scores between time 1 and time 2. So how are we going to conceptualize these problems? Everyone, do you understand the basic idea of what's in front of you here? We have 5 people. We measure their before and after scores, and we're going to see if they're different from people who don't have any change. All right, my hope is that it's so far so good. And so let's get into the basic concept here. We'll start, as we always do, by parsing the problem in step 1. I didn't write that out. So we'll parse the problem. And so I think I'm going to write it in, I think I'm going to write it out here. So let's do it in typing instead of my messy kind of writing. So population 1. We're looking at people whose, it's always weird phrasing in this test, people who whose scores reflect a training program. And for population 2, people who have no change in scores before and after. Just put in that same time frame. So in essence, we're comparing people who had this change program with people who didn't have the change program. We stated a little strangely, and I'm not going to be that picky about it here. It's just because it's a little bit weirder premise. Our dependent variable, what are we measuring? Well, we're measuring attitude toward masks. So we do that in the same way, a better attitude toward masks. Our tails, same thing. We are looking to see if they have a better attitude. So this suggests that we're doing a one-tailed high. We're looking for a score in that high end of the distribution. And this is how we're going to state our hypothesis. Well, in a nutshell, we'd be saying, let's see if I could just write here. Our research hypothesis would be for the mean difference for population 1 would be higher than the mean difference for population 2. Now, one odd assumption that we make about these people who have no change is that the difference between their before scores and their after scores is 0. So we could also say, or the mean difference for population 1 is greater than 0, because we're assuming that these guys have no difference between time 1 and time 2. The research hypothesis is the opposite of that. We will just say the mean difference for population 1 is not greater than 0, or easier still, we could write the mean difference for population 1 is equal to 0. There's no difference before and after. So this seems a little different. Again, we're just looking at the average difference between time 1 and time 2, and that's in a nutshell what we're doing. Everything else for this entire rest of the process is, except for one step, is just what you did before in the one sample t-test. So we're going to go ahead and solve this problem. First off, we have to do an important calculation. We have to calculate the difference. We just do this by taking the after scores minus the before scores. And so that's what we're going to do for each of them. So just so we save a little space here, I'm going to actually just erase what I wrote there and give myself a little bit more room here. There we go. So the difference, let me write it above, is just after score minus before score. So we're going to do 19 minus 15. And I think I'm going to keep this in red, equals 19 minus 15 equals 4. 17 minus 14 equals 3. 12 minus 11 equals 1. 16 minus 16 equals 0. 11 minus 15 equals, 15 minus 11. I started to do all these in reverse. It doesn't matter which way you go, a difference is a difference. The only reason it matters is that you'll be easier able to tell whether your end result is higher or lower. So in the end, though, your t-score will be the same whether you go before minus after or after minus before. 11 minus 12 is -1. 16 minus 16 is 0. And 15 minus 11 equals 4. At this point, we're done with these data. We no longer need them because everything else we do for our calculations relates to these different scores that we calculated. So let's tidy this up a little bit so that we can use these data effectively. So the difference is, in this case, I'm just going to write these a little more neatly. These are the scores we're going to use. For person 1, their difference score is 4. For person 2, their difference score is 3. Person 3 is -1, person 4 is 0, and person 5 is 4. So now we have calculated out. And now we're just going to do the t-test just like we did before. So I'm going to take and this is where we'll work with our data. And so let's go ahead and get our basic start for step 2. So step 2, we do just as we did before. We describe the comparison distribution. And we do it just the same way as we did before. We have to do the center, the shape, and the spread. The center is the mean, is the population mean, but it's the mean difference for the comparison distribution for population 2. This is what we're comparing. And we assume that population 2 has no change, no difference. And so the center is always in this test going to be 0. The shape, we're still using the t-distribution because we have no standard deviation given. So it's going to be the same as before, the t-distribution for, and we calculate degrees of freedom in the same way. Let's go ahead and write down our basic info here. Our basics, now we're using this data right here. So our basics, well, we know how to get n, the number of people, 1, 2, 3, 4, 5 equals 5. We know how to get degrees of freedom equals n minus 1 equals 4. We know now that the population mean for the comparison distribution, the mean difference between the before and after scores for the comparison distribution is 0. There's no difference. We're comparing this group who had this mask awareness program, we're comparing their change scores, their different scores, with this group who's had no change. And finally, we have to calculate the sample mean. And these are the mean differences. And that is just the sum of all the differences. I'll write diff there so we remember, divided by n. And if we sum all of those up, we find that that equals, if we add all those differences up, let me see here. Yes, if we add 4 plus 3, we get 7 minus 1 is 6 plus 4 is 10 divided by 5 equals 2. So our mean is 2. So now we have a lot of our basic information. And our t-distribution is for degrees of freedom equals 4. Excuse me. For our spread, we're still going to use the standard deviation for the distribution of means. So we're going to do just what we did before. And we're using these difference scores, of course. We don't need to keep stating that because you know it right now. This is going to be our column, our means. So let's go ahead and do just as we did in the one sample t-test. Let's estimate the variance for the distribution. And we know that another way to say variance is to say S squared. For me, sometimes that seems confusing because I always think I should do a calculation. So I sometimes like to just write out variance. And we know that when we say estimate instead of calculate, that means use degrees of freedom, not N. That's what that word estimate means. So it's the same basic formula that we've had from the start for calculating standard deviation. First, we calculate the sum of squares, which is the sum of all the deviations. So x minus m, but we're still using difference scores for each of these. So we could put x difference, we don't have to, but the difference scores, just so we remember. And because we're estimating, we know now that we have to use degrees of freedom. And so let's go ahead and calculate all of those deviations. So our x's now are the difference scores. So I'm going to label this column a little bit differently here. I'm going to label it X because these are our scores. And they are our difference scores because that's what we're going to use. So that's the difference between the first and the second. Now we just go ahead and we subtract our mean. So let's write the mean in, and I'll just indicate, again, these are the difference just so we don't forget what we're doing. And that is 2. So I'm going to put the 2 in throughout. And we know how to calculate those deviations. We know that the deviations is the same as x minus m. And I'm not going to write that little difference in now because we know that we're using those difference scores. And so 4 minus 2 is 2. 3 minus 2 is 1. -1 minus 2 is -3. 0 minus 2 is -2. And 4 minus 2 is 2. Those are our deviations. And we know that the sum of squares, which is what we're solving for right now, we have to square those deviations. I'm just going to write the asterisk here to indicate that we're squaring those deviations. 2 times 2 is 4. 1 times 1 is 1. -3 times -3 is 9. -2 times -2 is 4. And 2 times 2 is 4. That's it. And so I blundered here and wrote this in too soon. The sum of squares is just x minus m squared. And in this case, it is the sum of four plus 1 plus 9 plus 4 plus 4. And that sum of squares is equal to 22. We know that our estimated variance is equal to the sum of squares divided by degrees of freedom. And here is where I should have written that degrees of freedom in, because the sum of squares doesn't divide. So the sum of squares divided by degrees of freedom is 22 22 divided by 4, which equals 5.5. So here is our variance. We just, same as we did in the one sample t-test. Now we just need to compare apples with apples. I'm going to write this out this time just so there's no confusion. We estimated the variance for this distribution, but now we need to get the standard deviation for the distribution of means. So I'm going to put a note in here. We can't compare n equals 1 with n equals 5. So we calculate the standard deviation for the distribution of means, sized n equals 5. That way we'll be comparing the same thing with the same thing. So let's write this, calculate the standard deviation for the distribution. Let me write this out too. SM, we're going to calculate SM, and that is going, what that means is the standard deviation for the distribution of means. And that is just that same formula we've been using. We take the variance, I'm going to write it out right now, the variance divided by n. Let me just write this out even a little bit more clearly. We're calculating out this, the variance for the distribution of means, which is equal to the variance for the distribution of individuals divided by n, which is equal to, here is this number, the 5.5. So we're going to fill that in here. 5.5 divided by 5, which equals 1.1. We know that variance, standard deviation, we have to take the square root because what we actually need is the standard deviation. And so we know that we have to just take this variance, excuse me. We know that the standard deviation for the distribution of means is equal to the square root of the variance for the distribution of means. And that equals the square root of 1.1, and that equals 1.048809. That's what we're going to use for our calculation. All of this that we did was for spread in step 2. And we just did 2 steps. We estimated the variance, and then we calculated the standard deviation for the distribution of means. I can fill in this number, 1.05, and I can draw this distribution and fill this in so we know if what we're doing makes sense. So our comparison distribution is a standard deviation for the distribution of means. We know that the z-scores, excuse me, the t-scores fall as they always do. Here, let me write the normal standardized scores. We know this is going to be a t-score of 0 right in the middle. We know that 1 is going to be right about here. We know that 2 is going to be right about here. -1 and -2. If we fill in our scores that we just calculated, we know that our comparison distribution for population 2 has a mean of 0 also. And this means how we interpret this is no change. No change from before to after. That's what the 0 means. We know that now we have this standard deviation for the distribution of means of 1.05. For the sake of easiness, I guess I'll put 1.05 and I'll round to 1.1. So 1.1 and another 1.1, 2.2, negative 1.1, negative 2.2. So even though we have our standardized scores are falling in this orange scale that I've written, these are the scores, the difference scores that we're looking for. So if the difference for our any difference that falls within the center is like not more than 2 points away from the mean. So we're looking for, again, those change scores, those difference scores. We're no longer looking for just plain old scores, and that's why this one looks kind of weird. All right, if we continue on to step 3, we look up the cutoff point in the very same way. We still have only 4 individuals, or 5 individuals, or 3 degrees of freedom. So we're going to use that same chart that we've been using. We have degrees of freedom equals 4, and I didn't state the alpha, I don't believe, but we're going to say alpha equals 0.05. And we stated earlier that we were looking for a one-tailed test, and we were looking for high. We were looking for an improvement in the scores in the attitude toward mask wearing. So the cutoff point for that, using our calculator, I think it might be the same as what we already have up there. Let me get it. Here's our calculator. We had 0.05 and we had 4 degrees of freedom. So we haven't changed. So in this case, our cutoff point is still going to be 2.13. We don't have to put the negative sign in front of it because we are looking now for a value that's up on that upper end. So it's going to be equals 2.13. And let's draw that in. We were looking for we're looking on the Z distribution now. So here's our 2, and here's our 2.13. So our cutoff point is on the upper end of the distribution, 2.13, and we're looking for a value that's going to fall in this upper tail somewhere. And this value, again, will represent the difference scores for these individuals, the mean difference scores between attitude in time 1 and attitude times in time 2. So that's what we're looking for. Step 4, we calculate the t-score. And it's done the same way as before. We are taking the mean, and I'll do it by calculations over here to keep it neat. So calculate t. And the calculation for the t-score is just the same. We're going to take the mean for our sample, and of course this is the mean difference implied, minus the mean for the population, and divide by the standard deviation for the distribution of means. Our sample mean is 2, what is our sample mean? Way up here. I didn't calculate it out. I did calculate it out, but I didn't write it down. The mean for, I just didn't write it down. The mean is 2. I wrote it up here. And so equals 2 minus, and we know the population mean is 0, divided by 1.048809. And that equals 1.906 And we can write it over here where our answers are. T equals 1.91. We can plot our t-score up on our chart. I'll do it in purple. 1.91, I can see here is the standardized score 2. 1.91 is going to be T equals 1.91. Because our t-score is not to the extreme of the cutoff point, and because it's not in the shaded region, our step 5 is that we fail to reject HO. If we fail to reject HO, then it stands. The mean difference and so we conclude the mean difference in attitude toward masks after a mask awareness program was not different from 0. That's a really awkward way to say it. I think if I was going to actually write this up in a paper, I'd probably write people who took the mask awareness program this is probably how I'd write it more in English. Program had no change in their attitudes toward masks. Some did, some didn't, but overall, the difference was not statistically significant. I would write then the statistic. I think this second way is a clearer way to express this conclusion. I would write T, and then I'd write degrees of freedom. And then I would put the t-score, which was 1.91, and I'd simply write NS, not significant. Didn't pass our test. All right, what questions do you have on this type of problem? This is called, let's give it a name now. This is in the second part of chapter 7, and it's called the paired samples t-test. There are some other names that we give that this test is given. It's because we have pairs of data for the data come in pairs. And so we're calculating these differences. And I hope you saw that the only difference in this whole process was that we were using these scores instead of the actual scores that were given to us. Other than that, the whole process was identical. So any questions on this?
No.
All right, I put up some practice problems, and what I'm going to do is put up the answer key for each problem. So I'm going to want you to solve a problem and then check the key right away, and then do the same, and then find out if you made a mistake, what did you do wrong? That's what's going to help you in your homework. Please redo the homework if you would like to. I want to check you guys off as being done with the one sample t-test, and meet with me if you need to. And I'm hoping to meet with a little group in person to get everyone right on the page with this. I think that would be a really good way. And I would like to try and find a time to do this with you. I'll linger around here for a minute in case you have anything. Otherwise, I'll say goodbye and let you sign off and go about your day. And thank you for coming. Thanks, Chardon.
See you later.
Thanks, Kiana, Kyle.
Dr. Ross, this is Yolanda.
Hi, Yolanda. How are you?
I'm doing okay. I like to meet as a group or the group you want to do whenever you get together.
Yeah. Is there any chance like a Friday would ever work for you?
On a what?
On a Friday afternoon?
Yes, that would be good.
I think I'll plug that in. I think other students might be available too. I think that would be a good time to meet. So let's see if we can meet this Friday. And I'll send out a message right away. And would like 1 o'clock be good?
Yeah.
All right. I'm gonna plug that in.
I'm not even looking at my schedule, but I'll let you know. I'll look at the schedule as soon as I signed off, and I'll just email you.
All right, I'm going to put out a notice and just say, you know, can we meet in the classroom at 1 o'clock on Friday for those of you who'd like help with any kinds of questions.
Hmm.
All right.
Okay.
All
Thank
right,
you.
sounds good. See ya.